This is screencast 3 for week 4 for 571. As you can see on the screen, after my mess up, I think I got it right. This is Z upper, and of course you can tell that by the plus sign, and Z lower by the minus sign here, because the rest of the two formulas are the same. And so to get the out-of-control ARL for a k-sigma mean shift, you divide the sum of the probabilities in the two tails. You divide that sum into 1. And just to give you a picture of what's going on, here's Z upper, and here's Z lower. See, and what you're doing is you're adding up these two areas, and then you're dividing that sum of area into 1. So that will give you a function of how many subgroups you will see on average before the chart does what it's supposed to do, and that is tell you that you have a problem. So, a couple of general comments. First, most business manufacturing process metrics are not normally distributed. Most of them, of course, are positively valued. And right off the bat, that means they can't be normally distributed, because the normal distribution has support on the real line, i.e. any value of any real value, any value on the real line is possible under the normal distribution. But if you're measuring a dimension, you're never going to measure a dimension smaller than 0. If you're measuring a temperature, you're going to have a lower value, say the temperature of your soldering iron, and you have this automated soldering system, and so you're monitoring how hot the soldering iron stays at. Well, you're certainly not going to ever see a soldering iron temperature below room temperature. So you have a variable which is guaranteed to have a lower limit, but the normal distribution doesn't have any lower limit. Also, you're going to rarely see a metric that has no upper limit. On a critical dimension, it's very unlikely, if the blueprints call for a 1 inch engineering value, you're never going to see 2 inches. You might see 1 inch, 3/10,000ths of an inch, or 1 inch less, 3/10,000ths of an inch. So there's going to be a very tight interval of possible values. All these facts point to the fact that you're not going to be seeing a normally distributed metric. So the central limit theorem is your only hope. In using the normal distribution to find control limits for an X bar chart. So recommendation. Draw the normal QQ plot using the K stage 1 subgroup means. If non-normality is evident, try a power transformation. So what's going on here? Well, here's a QQ plot. Here are the z-scores, and here is the sorted data. So you're going to plot as per the homework problem in Ryan. You're going to plot a bunch of points, and this point here, for example, is z I comma x bar I, where the parentheses means sorted, and this is for k equaling, for I equaling 1 to k, the number of stage 1 subgroup means. So how can this plot go sadly wrong? Well, this is the line. The one-to-one line is the line that indicates that z equals x. So this is the x equals z, otherwise known as the one-to-one line, aka. As long as the x's are really close to the z's, you're good to go. You've got normality. But a lot of times you'll see this. Simply because x isn't going to get any bigger. But the z's say, no, they can get bigger. And so what you have is a trailing off. So it's okay for a while, and then it trails off. This is non-normality. The other thing you can see is the opposite, where you're going along and you start getting x values that are bigger than the expected value. So these are expected x values. Keep hitting that switch. And as long as the expected, the z's, the sorted z-scores, are good stand-ins for the x's, then the assumption of normality is okay. See, these are z-scores, so they're coming from the normal table. But when you see one of these two patterns, that's implying that all is not well. So the first thing that most statisticians would recommend that you do to fix this issue is apply a transformation. So instead of measuring, instead of computing the average of x, compute the average of x raised to a power. and this is this one I have right here is called a power transformation. And this is wrong. So we transform from x to x prime. This is red, x prime. Because the little dash is referred to as the prime. And you have to hunt for the best value of lambda. Now, of course, you can kind of get a sense that this game may not so let's say you do a one-dimensional plot of x, and you get when you just look at x, you get a whole bunch of points that are way out here. If you want to take these points and bring them back, then this will suggest that lambda might want to be some value around 0.5, or what you're doing is you're taking the square root of the x's. And that would correspond to, this would correspond to this condition, where the x's are getting too big for what the normal distribution thinks they ought to be doing. So this is only going to work if you have radically large x's coming at you every once in a while. Because look, lambda's imprisoned between 0 and 1. So if you have x's that are not big enough, like these guys, well then lambda should be bigger than 1. You want to inflate them, you want to make them bigger. But you got to make sure that here is the value 1.0. Or you do this. X prime equals quantity x plus 1 raised to the lambda, lambda bigger than 1. Now that'll work just fine. See, what you're doing is you're forcing x to be a little bit bigger than 1. Remember, when you raise a number below 1 to higher and higher powers, the result gets smaller, which is not what you want in the case where the x's aren't getting big enough. So what you want to do is make sure that everybody's forced to be bigger than 1. So as long as x never goes negative on you, because it's a metric where you've designed it to where it can't be negative, this guy will work out really well to solve this problem right here, where the x's aren't big enough. See, so you got to become kind of a mechanic when you start hunting for a transformation that is going to give your normal QQ plot a better appearance. If you don't, then the false positive rate for your control chart is unknown, because now you're using limits that were derived under a distribution that's not holding for your subgroup means. So why do I say that the central limit theorem is your only hope? Well, if n gets much bigger than 10, then the central limit theorem will kick in, as I like to say, and cause x bar I to be distributed approximately normal. Well, that's why the central limit theorem, as I said in earlier lectures, is so important, because Schuhart depended on it to argue for his upper control limit, lower control limit being equal to x double bar plus and minus 3 sigma hat x hat, because this assumes normality. But he knew darn well that in the real world, lots and lots of real industry/business processes were not normally distributed. And he said, well, that's okay. I don't care about x itself. All I care about to build my control chart is X bar, averages on subgroups of size n. So if large n is impractical, transformations may be required. So you might get backed into a corner. Why? Because of your managers, not statistics and what I'm saying here with Ryan at all. Management might say, we're really bored with you telling us that you need n being 15, because you've gone on and on about how if it isn't 15, then the X bars are giving a QQ plot which doesn't appear normal. The reason we're bored with that is because there's no way we're going to let you build 15 units before you evaluate for signal. We've got to know every other unit. Why? Because we're making super expensive avionics circuit boards, and if we have a problem, we want to know about it right away. So for our operation, either we don't run a controls chart because we can't afford to wait that long, or we run a control chart with n set to 2. And you do whatever magic you have to do to get us there, because we can't wait for 15 per data point. So that's backed you into a corner where you've got to know something about transformations. You can't get out of it. And there's no fancy software that's going to get you out of it. You've got to start hunting for a transformation that'll make the QQ plot on the X bars look sort of normal. Otherwise, the control limits are wrong. Wrong control limits mean wrong false positive rate. A wrong false positive rate might mean that you've set your limits way too wide and your chart won't squeal when it should. That's worse than the chart squealing too often. Not squealing enough implies that a true out-of-control event will go unnoticed. You could cost the company serious money in recalls and loss of customer goodwill by doing that. Talk to the folks at Takata. That company is basically on life support. And it's been traced to the fact that they had no internal quality control program. They depended, like I said before, they depended exclusively on complaints on their products coming from outside the company. And sure enough, complaints came from every major manufacturer practically in the country, in the world. And now I think now the Japanese government is keeping them alive. Okay, there are many other transformations, but the power one is one to get you started. If you wanted to go into it a little deeper, you could type in statistical transformations into Google. By the way, you can do a chi-squared QQ plot to check the chi-squared assumption of S1 squared, S2 squared for the S chart. Probability limits. And if you want to nose around my G drive, you'll find a PDF file out there that tells you exactly how to do that. But it's not something I'm going to be holding you to for exams. Okay, well, those are some of the notes. We've got another problem now. We put our management hat back on, and we ask the question, what to do if we get signal. This is a management question. Excuse. So we've gone through all of the statistics and probability to allow us to figure out how to construct a chart that gives us signal with a known false positive rate. So management says, all right, we're listening to your elevator pitch on putting in a quality control program, and we like what you're hearing, and we're at the 20th floor, and we got to get to floor 40. So we got a big question, and that is just exactly what do you want us to do if we ever do get this signal, which you keep talking about. And you say, glad you asked. What you got to do is have a pre-built out of control action plan. Or OCAP. So what's that? It's also called a reaction plan. And we are talking training. Core idea here is that what you're going to do is you're going to train your workers to initiate a predetermined plan should one of your control charts squeal. Well, it could be a false positive. You don't know that. You can't ignore a signal off of a control chart. If you ignore a signal off a control chart, there's no point in running the control charts in the first place. So, an example that I will be putting up on the next screencast comes from this website. Datalyzer.com. www.datalyzer.com. And what they do is sell software to connect a process, FMEA, called a PFMEA, to an out-of-control action plan. That's very cool. I mean, to be blunt. Some of these smaller companies in the software world, you know, you'll open the paper, and every couple of weeks you see some giant corporation like Microsoft has just bought some small software company. You see Oracle doing this. You see Google doing this. What's the deal? Well, it turns out that a small group of entrepreneurs and visionaries got together and they built a small company doing something that no one else was doing, but they knew there was a market for. And then after a while, the big dogs notice this company and they buy them out. They say, come work for us, we're going to own you, and we'll pay the people who started the company buckets of money to sell their company to us, and then we'll have instant capability. That's exactly what might happen in the dreams of the people who own this outfit called Datalyzer, which I will continue on my next screencast.